Beets are pretty interesting, and not just because about 50% of people who eat them produce colorful waste. For one thing, they are an excellent source of sugar, as Mr. Berry said. Their high sugar content was first noticed in 1747 by Andreas Marggraf, a German apothecary who had been using beets as a laxative. He was struck by their sweet taste. One of his students, Franz Karl Achard, decided to grow several beets varieties and see which produced the most sugar. By 1802, a pilot sugar beet refinery had been built in Prussia. The real stimulus for producing sugar from beets arose during the Napoleonic Wars. The British had blockaded French ports, cutting off sugar shipments from the Caribbean, so Napoleon ordered his minions to find a way to make sugar beets refineries efficient. One Jules Paul Benjamin Delessert succeeded in finding an effective way to extract sugar from beets, and he was rewarded with the Cross of the Legion of Honor. Soon 40 beet refineries were supplying France with sugar, and that number expanded to 250 by the mid-1920s. Sugar went from being a luxury item prescribed as a sedative for insomniacs to being a widely available commodity. To this day, beets are a major source of sugar in Europe. You would be sprayed with a hot solution containing irritant chemicals known as benzoquinones. In all likelihood, this would be a memorable, if unhappy, experience. Given their ability to discharge these chemical bombs when threatened, bombardier beetles are aptly named. Beetles differ from other insects in that they cannot fly instantly. They store their wings under covers, which they must retract before they can take to the air. Sort of like Clark Kent having to shed his everyday clothes before becoming Superman. Since beetles cannot fly to safety the second they are attacked, they have evolved emergency defenses to deploy while they are prepared to flee. Scientists have studied the African bombardier beetle extensively in order to understand its remarkable defense system. When attacked by predators, mostly ants, the beetle unleashes bursts of hot chemicals with audible detonations. The spray originates from a turret-like appendage under its abdomen, which the beetle maneuvers to achieve remarkable target accuracy. But the truly amazing thing is the chemistry of the spray. The beetle concocts the irritant chemical just prior to launch by mixing the contents of two separate glands. One contains hydrogen peroxide and hydroquinone, and the other harbors a blend of enzymes known as catalysis and peroxidases. That reacts with hydrogen peroxide to create oxygen, gas, and water. When the contents of the two glands mix, oxygen forms and reacts with hydroquinone to convert it to benzoquinone. This reaction is so highly exothermic that the chemical mixture can reach to a temperature of 100 degrees or 100 degrees Celsius or 212 degrees Fahrenheit. Pressure due to the buildup of oxygen then causes the hot mixture of water and benzoquinone to be expelled with a pop, much to the woe of any attacking ants. A bombardier beetle can launch up to 20 of these chemical bombs before running out of ammunition, but by that time it will have succeeded in unfurling its wings and it's ready to leave its attackers wallowing in its toxic wake. Aristotle used goat urine and Hippocrates recommended pigeon droppings. For what? Both of these substances were reputed to cure baldness. Most men don't find baldness an appealing trait, despite the stories of bald men's sexual prowess, stories like Initiated by Bald Men. Throughout history, men with bald pates have tried anything and everything to stimulate hair growth. The ancient Egyptians applied rancid crocodile or hippo fat, rationalizing that if it smelled bad, it must be doing some good. Oh gosh, it wasn't. In order to coax Julius Caesar's dormant hair follicles into action, Cleopatra experimented with a goo made of ground horse teeth and deer marrow. When this didn't work, she traded him in for Mark Antony. Bald Victorians brushed cold tea, followed by citrus juice onto their scalps. In farming areas, chicken droppings were used, and baldies even persuaded cows to lick their heads. Electric combs, suction cups, and paint thinner were all tested as baldness remedies. There is no end to it. Infomercials push shampoos with special emulsifiers that clean follicles as if baldness were due to plugged follicles. Others promote what amounts to a spray paint that covers bald spots. The truth is that only Rogaine, minoxidil, rubbed into the scalp, and Propecia, finasteride, taken orally have shown any hair growing effects, but these effects are not very impressive. The toxicologist's refrain is, only the dose makes the poison. The most innocuous substances can be deadly in high doses, including water. Believe it or not, there is such a thing as water poisoning, and it can be lethal. If body fluids become too diluted, then sodium concentrations in the blood drop dramatically. Sodium is an essential mineral in the body, and it plays a critical role in the transmission of nerve impulses in the brain and the muscles. Our bodies regulate the concentration of sodium in our blood by moving water in and out of the blood. If you have a high sodium concentration, then water moves from your cells into your blood, increasing your blood pressure. As water moves from your brain cells into your blood, your brain actually shrinks, and you may experience confusion and seizures. If your sodium concentration is too low, then the reverse happens. Water moves out of your blood and into your cells. This can be disastrous to your brain, since as your cells absorb water, your brain swells. This in turn can lead to lethargy, loss of consciousness, and even death. This isn't merely a theory. Excessive water consumption has actually killed. In a truly disturbing case, the parents of a 4-year-old were charged with child abuse and murder. The Utah couple felt that their newly adopted daughter wasn't bonding with them properly. Acting on what they claimed was the advice of a misguided alternative therapist, they tied their daughter's hands behind her back and forced her to drink huge quantities of water. The idea was that such therapy would transport the girl back to infancy when she consumed nothing but liquids. In this infantile state, she would be reprogrammed. The couple and their lawyers built their defense on this version of events, accusing the therapist of malpractice. But the prosecution insisted that no one ever recommended such hydrotherapy to the couple, and that the adoptive parents were in fact punishing the child for stealing some Kool-Aid from a sibling. We don't know what really happened. Was this an instance of alternative therapy gone awry, or a case of child abuse and murder? One thing alone is clear: the unfortunate child died of water intoxication. Erasers have an interesting history. When the Europeans first arrived in South America, they discovered natives making interesting use of tree sap. They were shaping the wet latex into balls and allowing the balls to dry, thereby creating the world's first bouncy balls. The explorers took some samples with them to their homes, and one found its way into the hands of the brilliant English chemist Joseph Priestley, who found a use for the material. It would neatly rub pencil marks off paper. He called it the rubber. In North America, we call it the eraser. How does it work? Through the physical action of abrasion. This pencil deposits a thin layer of graphite on paper, a layer that lifts off easily when gently rubbed with an eraser. The trick is to remove the graphite without damaging the paper. So we do not want an eraser that is too abrasive, and chemists have worked on this problem, and they have improved on the original rubber. For one thing, they have vulcanized the rubber, that is, they have treated it with sulfur. This increases its resiliency and reduces its rigidity. They have also added a fine pumice powder made up of about 75% silicon dioxide and 25% aluminum oxide to the rubber, giving it the correct abrasive quality. This pumice is the stuff they use to make sandpaper, but they grind it much finer for inclusion in paper and erasers. Why do erasers not work as well on ink? Unlike graphite, ink is absorbed into the paper, so rubbing the surface isn't enough. Deeper penetration is needed, which damages the paper. Why is the traditional eraser pink? These days, most erasers are made of synthetic rubber, which is a polymer. Manufacturers add a chemical called an accelerator to the rubber during the production process to help join the monomers, or small molecules, into a polymer. The original accelerator was pink in color, and today's manufacturers uphold the tradition by using a pink dye. Just like everything else, erasers have changed with the times. Most of us, when we think of polyvinyl chloride or PVC, we think of vinyl car roofs or the old-fashioned LP record album. But this synthetic polymer can also be formulated into erasers. To make the material soft and pliable, manufacturers add a plasticizer, such as diacetyl phthalate, to the mix to improve abrasion. They stir in some calcium carbonate or chalk. Vinyl erasers are gentler on paper than rubber erasers, and they have some other admirable characteristics as well. For example, white vinyl erasers are good for cleaning ivory. And people who are allergic to latex need not worry about reacting to a vinyl eraser when rubbing out their mistakes. There is, however, some cause for concern about the environmental consequences of the phthalates. They have been accused of having endocrine disruptive effects. In the 1960s, scientists examined the memory of worms, conducting a series of highly publicized studies that focus on feeding worms a special diet. What was that diet? Other worms. James McConnell of the University of Michigan, who would eventually publish a journal called Worm Runner's Digest, got the ball rolling by showing that flatworms can be conditioned in a fascinating way. McConnell claimed that if he exposed a worm to light followed by an electric shock, the worm would alter its slithering path. His worms associated the light with the shock and learned to avoid the path that delivered the shock when the light was turned on. McConnell also knew that if you cut a worm in half, both halves would regenerate, and he wondered which half would retain the memory. To his amazement, he discovered that both did. The researcher had to conclude that memory was somehow stored in molecules throughout the worm's body. Then McConnell was struck by another idea. Grinding up trained worms, he fed them to untrained worms. The cannibal worms began to avoid the light as well. Apparently, memory had been transferred. This astounding observation stimulated much research, not only in worms but also in fish, mice, and rats. Unfortunately, other researchers could not reproduce McConnell's results, and as yet, nobody has isolated memory molecules. But the worm research did have some interesting spin-offs. Mice that were fed the brains of livers of other mice subjected to stress. Researchers have rolled them around in glass jars, learned to associate a light stimulus with electric shock faster than other test animals. It seems that stress hormones transferred by diet enhance learning. Maybe someone should examine whether humans who dine on stressed factory-raised chicken are smarter than people who favor free-range, carefree poultry. Maybe they are, since they are unwilling to pay higher prices for chicken that has no clear superiority. Of course, someone is bound to point out that smart people don't eat animals in the first place. Maybe we should stretch broccoli and see what happens. Luminous paints, such as those used on watch dials, contain chemicals that absorb light and re-emit it over an extended period. The phenomenon was first noted in the 1500s when stones discovered near Bologna, where they were found to glow after exposure to sunlight. Some would glow in the dark for years after they'd been heated intensely in the presence of carbon black. As you can imagine, this quality was very attractive to alchemists and others who dabbled in mysterious arts. The stones turned out to be barite or barium sulfate. When heated with carbon, the barium sulfate converted to more luminous barium sulfide. The discoverers of these rocks dubbed them Lopus Solaris, or sunstone. Since then, many other light-storing compounds have been discovered. One of these, calcium sulfide, is commonly used to create theatrical effects in luminous dials. Whether the watch dial glows or not depends on the intensity of the light to which it has been exposed during the day and on the amount of time it has spent in darkness. The glow fades as time passes. This phenomenon is amenable to many applications. A few years ago, glow-in-the-dark boxer shorts ablazing with the word "yes" were big sellers. Then there are glow-in-the-dark condoms which gleam for the full 15 minutes after a few seconds of exposure to bright light, giving the expression "rising sign" a whole new meaning. And finally, there is the glow-in-the-dark toilet seat. Its inventor, a fourth grader, won a prize for it at an inventor's competition. The judges were impressed by the idea that they could keep people from stumbling around their dark bathrooms in the middle of the night. Sounds like a great idea. The glowing seat helps men to find their target and women to see whether the men have returned the toilet seat to the down position. Roosters crow to attract chickens, of course. Chickens have been around for roughly 5,000 years, and the general opinion among evolutionists is that way back when, roosters crowed all the time because, like men, they were ready to indulge in carnal pleasures at any hour. But the crowing sound attracted not only hens, but also predators. So roosters took to crowing at low light times of day, dawn or dusk, when they were harder for predators to see. Truth be told, some roosters don't restrict themselves to crowing at dawn or dusk because these days their predators are scarce. We tend to notice the early morning crowing, however, because there are a few competing sounds at that hour. Incidentally, chickens don't need roosters in order to produce eggs. They lay them all the time, but of course these eggs are not fertile and will never hatch. To produce fertilized eggs, a chicken must mate with a rooster, and that's where the crowing comes from. We generally mine salt, but we can also produce it by evaporating seawater from special evaporation ponds. These ponds are often dyed a stunning blue color. Why? To increase the rate of evaporation. Just think about how you feel on a hot summer day if you happen to be wearing black. The black absorbs the heat very efficiently, making you feel quite uncomfortable. White reflects heat. This explains why people tend to wear white clothing in the tropics. Blue is also very good at absorbing heat, although it's not as good as black. But there exists no appropriate economic black dye that we can later remove from the salt residue. We can, however, easily remove the blue dye, triphenylethymine, from the salt once we've purified it. Now, why do we need so much salt that we have to evaporate seawater? This salt is not destined to be sprinkled on our French fries. It is used to produce chlorine and sodium hydroxide, two of the most important industrial chemicals. Passing electricity through salt water converts sodium chloride to chlorine and sodium hydroxide. This process is at the heart of a huge industry. Indeed, it consumes more electricity than any other industrial process, save for extracting aluminum from its ores. Ornamental ponds are sometimes dyed blue as well. This has nothing to do with salt production. It's a measure to prevent algae growth. Algae require sunlight, and the blue dye absorbs the light, keeping it from stimulating algae growth in the pond. Believe it or not, it's spider silk, the stuff spiders use to weave their webs and catch their prey. Spiders also use silk to hang from a support and swing back and forth as they build their webs. Their silk fibers are at least 4 times as strong as steel fibers of the same diameter, stronger even than fibers of Kevlar, the synthetic material used to make bulletproof vests. Not only is spider silk strong, but it's also stretchy. It has to be, otherwise flying insects would just bounce off of it. The properties of spider silk reflect its internal molecular structure. All such silk is made of protein, but spiders produce a variety of proteins with which to spin it. Proteins are built of amino acids, but the specific properties of a protein are determined by the variety of amino acids that join together to form the protein chain. Scientists have found 6 amino acids, namely glycine, alanine, proline, tyrosine, serine, and glutamine in spider silk. Chains that have long sequences of alanine units can pack together very closely in what we call beta sheets, and they are responsible for the strength of the fiber. Flexible chains have sequences of amino acids that allow them to fold and act like miniature springs. Amazingly, spiders can customize their silk. They have several silk glands, and each has a different secretion. They can blend the various proteins that their glands produce to create a silk that's suited for a particular purpose. Unfortunately, we cannot raise spiders in captivity to produce silk. Aggressive creatures, they will attack and eat each other. Bacteria, by comparison, are more peaceful, and they can be goaded into making spider silk. The DNA sequences that make up a spider genes that code for the silk protein have now been identified. When these genes are inserted into bacteria, they produce spider silk, but not in industrial quantities, and that's the problem. In an attempt to solve this problem, Montreal's Nexia Biotechnologies implanted spider silk genes into goats, and the proteins needed to make the silk showed up in the goat's milk. Eventually, the research may allow us to fabricate superior bulletproof vests and super strong fabrics and cables, not to mention artificial tendons and ligaments.